Bioenergetics. This looks at those reactions, exergonic, endergonic. What drives these reactions? ATP, right? Where do we get ATP? From cellular respiration, metabolism. Okay. We build things up, we break them down, and we build things back up again. That is what cellular respiration metabolism is. All right. So what are these reactions? Well, we have two different types of reactions, right? Exergonic and endergonic reactions. Endergonic, endo, E-N-D-O, means to put in. Okay, put in. All right. So these are going to be chemical reactions that require that energy. All right. When we start looking at metabolism in chapter 5 here, hopefully in the next hour, we're going to see that we have to put in a little bit of energy, a little ATP currency to get things to happen. All right. And in glycolysis, that's the first step. We need an investment of energy. We need an investment of money, ATP, to help kickstart glucose's change into a 3-carbon pyruvate creature. In endergonic reactions, the products contain more free energy. Okay. So we have a energy of activation hill to get over, right? To get this thing to happen. Exergonic reactions, EX of exer, EX of exit. Okay. Release energy. I don't like cyan. No, I don't want that number. Oh, hell yeah. All right. These are going to be chemical reactions, again, that release that energy. These are going to be the energy, these are the type of reactions that really drive endergonic reactions, right? Exergonic, release it to help fund those endergonic reactions. And these type of reactions, products have less energy. Okay. In these type of reactions, you're breaking down something into their component parts. So you're making something smaller, okay? Or you result as something smaller. You start with something big, break it up into something that's really small. That's basically a catabolic type of reaction, okay? Where glucose is broken down into stuff that's smaller, stuff that really doesn't have a whole heck of a lot of energy. Carbon dioxide and water don't really have a whole heck of a lot of energy at all. Okay, and there you go. Okay, these are the type of reactions that help to fund endergonic reactions. And when we talk about we'll talk about this. Okay, cellular respiration, metabolism, all right, where we take glucose, C6H12O6, and some oxygen, and we can yield a good chunk of energy. All right, 32-ish units of ATP. And we'll talk about that in chapter 5. I believe that's 5. In the process, as we change this thing into various different forms, we get to release some energy. Until these things don't have a whole hell of a lot of energy. And they're removed from the system. Okay? Packaged up, exocytosed, right? Exhaled, removed from the urine. All this different fun stuff. All right. What is all of this? It's energy, right? These are going to be helping to create these units of energy, ATP, to help fund all of what we need to do inside of us. A resting metabolic rate or a basal metabolic rate is the bare minimum number of calories I need to shovel in my mouth to get me all of these units of energy. And it's around 2,000 calories is a typical satisfactory American diet. Okay. Maybe you do a little bit more. Maybe you do a little bit less. But 2,000 calories is about a typical diet. Okay. And I believe in chapter 19, they go over a little bit of those concepts and those numbers. I'm not going to ask you those numbers. Okay, so I'm just telling you right now if I don't say it later. What is a calorie? Amount of heat required to raise the temp of a cubic centimeter of water a degree Celsius. Okay, they are in units of thousands. Okay, and it's the big letter C. Small letter C is 1 calorie. To raise it 1 degree centigrade. Calorie with a big C is a centimeter of water, not a meter of water. So these are much calorie with small c is really small. It's really hard to fathom that. You would have to eat 200,000 calories. If I told you you had to eat 200,000 calories to maintain normal body function, you would look at me with your eyes crossed. Okay. If you've ever eaten 3,000 calories in a day, you know that that's a hell of a lot of work. All right. So we talk about it in terms of big C. Okay, not little c. They're coupled. I mean, this is gen bio boring nonsense. All right. Endergonic and exergonic reactions are coupled reactions. Exergonic releases it, and that helps to fund those endergonic reactions. Here is what the molecule of ATP looks like. Adenosine, some phosphates, okay. Three phosphates, 1, 2, 3. The great thing about this thing is that all we have to do is break that little bitty bond. Which bond? That bond right there. You break that bond, releasing an inorganic phosphate from the trio, and you get ADP and an inorganic phosphate, and you get that release of energy that is so necessary and so required. Okay? And there are a number of chemical pathways for which we can create this ATP. Okay? The calories that you consume to fund the body's ability to create all this energy comes from carbohydrates, primarily, fat, secondarily, and in a last resort kind of situation here, it comes from protein. So all that food that you guys are consuming come from those 3 macronutrients, those biomolecules. Okay? We predominantly only talk about carbohydrates, generally because that's its primary function. Okay. We will also talk a little bit about some fat production or fat utilization, in terms of creating energy. We'll look at a little bit of protein here in chapter 5, but that's not its primary function. Protein's function to help make things, make structures, to do a whole myriad of functions in the body. Only will protein be utilized as an energy source if you are, starving. Okay. So I guess you could be an intermittent faster and your body would kickstart protein use, but it's going to use fat first. So some fun conversation that we'll have here in a little bit. When we look at these reactions in cellular respiration, there are a number of going to be creatures that are going to be oxidized and things that are going to be reduced. If something is reduced, it gains an electron. Remember, electrons are negative creatures, right? Floating around in those little orbits. When we have chemical reactions, is the movement of these electrons from one thing to another that causes this negativity or positivity occurring, this reduction or oxidation. Oxidation, there we go, loses electrons, gets more positive. Okay, remember, electrons are negative. This is important for how things age. Okay, all of these chemical reactions are not equal. Okay, one thing is always going to be a little bit more positive or negative than something else. Okay, so it's never an even split. when that happens, we get these free radicals, right? Free radicals are molecules that have an open spot. And what's that open spot? That open spot is an open spot to have a reaction with something. And they never just sit there and be like, you know what, I'm just going to hang out here and be cool. They're always looking to go mess around with somebody because they have an open slot. And so if you get a huge number of these free radicals producing, that can ultimately lead to excessive wear and tear. Wear and tear on cell membranes, structures. And that's part of the aging process. Now, is some of that good? Hell yes. Oxidative stress is a good thing. It stimulates the body to try to be a little bit better. So a little bit of oxidative stress is okay. An excessive amount of oxidative stress is a bad thing. And that's what can lead to potential disease. Okay? Make you look older. Think of somebody who smokes. Okay? Exhaling all of that carcinogen gets exposed to the cells in the skin, right? Chemical reaction occurs. They lose some of that vibrancy, that resiliency, because of all the free radical accumulation. Plus, it's a carcinogen, for God's sakes. Stop smoking. Skin can rebound a little bit. Actually, the lungs can rebound a hell of a lot better than what that skin looks like on those individuals. And again, we have a series of these oxidation reduction reactions in cellular respiration, glycolysis, citric acid cycle, electron transport chain, where we have stuff giving away electrons, something picking up electrons, and we have this accumulation of these free radicals. Really, the biggest one that we're going to talk about, guys, is going to be this dude right here. Okay. Oxygen is a great electron acceptor. All right. We get a vast amount of movement of electrons when it comes with oxygen. That's why the mitochondria is so fantastic with what it does. It allows the utilization of oxygen to be that final electron acceptor to help ultimately create energy. Some of the most important players we have here are these dudes right here, NAD and FAD. These are some coenzymes. You get them from some important stuff that hopefully you should be consuming every day. Riboflavin and niacin are your B vitamins, B2 and B3. When it comes to an inability to get one of these vitamins, usually it's niacin is the potential issue. Riboflavin is not, it's found in a lot of foods, and it's not that difficult for us to get more than enough. Okay? If there's going to be an issue here, it's going to be niacin. There's its fancy name. I probably won't ask you the fancy name, to be honest. Nicotinamide adenine dinucleotide, and flavin adenine dinucleotide, NAD and FAD. That's what I'll probably ask. Okay. NAD and FAD are important coenzymes because of what they do. They go in, accept a couple of electrons, and they move them around. We will get electrons produced in a number of different parts of cellular respiration. These two guys here, NAD and FAD, help to pick up those electrons that get produced. And it escorts them to the electron transport chain, our huge yielder of energy for glycolysis, cellular respiration. Okay. FAD can accept 2 electrons there, so there's its FADH2. NAD can accept a couple of different electrons, NADH plus a hydrogen ion. So that's what these creatures are. Where do we make them? How do we make them? We make them from consuming our B vitamins. And remember, B vitamins are water soluble. Okay? These are water soluble vitamins. So you don't really store these things. There's not a huge reservoir of storing water soluble vitamins in the body.
So they just like to transport energy.
They transport electrons.
Electrons.
They transport electrons. And we're going to use those electrons to help harvest energy in that electron transport chain. There you can kind of see what they look like. I'm not going to have a picture and ask you to identify them, knowing what they are, their important coenzymes, knowing what they do, accept electrons, knowing how we ultimately form NAD and FAD, B vitamins, niacin and riboflavin, respectively. Those are important things to know. They're just here to give you a picture, to give you a frame of reference, to see what they look like.